go up to where it says File and click. Scroll down to Data, scroll to Analyze, and click. A new window will open. On this new window, click Data, select Moon, and I'm going to select Ganymede. The reason for choosing Ganymede is because it's a nice shape that can easily be seen, and it's a whole period. It's the easiest of the moons to analyze. Select Data again, scroll to Plot, then scroll to Plot Type, then to Connect Points, and click. You will now see a rough line drawing of the connected points. Go ahead and click on Data again, scroll to Plot, scroll to Fit Sine Curve, and then select Set Initial Parameters. Then I'm moving the new window that pops up so that it's out of the way. The first blank in the new window is called T0. This represents some place on the graph where it crosses from negative y values to positive y values. Click on the point where it crosses. In the lower left, you will see the x value for that point. Make note of it. You will also enter this value into the box that says T0. We marked where it crossed the x-axis on the way up, and we look for another spot where it also crosses the x-axis on the way up, and we click that point. Then we make note of this new x value. The time between these 2 points is the time that it takes Ganymede to go around Jupiter once. The difference between these two numbers is the number of days for Ganymede's orbit. Enter that value where it says period. Now we need the amplitude. Click on all the highest and lowest points on the graph and make note of those y values. These are estimate of the radius of the orbit in units of Jupiter diameters. Enter the largest of these values in the box that says amplitude. After you have entered all these values, click OK. At this point, you should see a sine curve that fits reasonably well through the data points. If it doesn't, double check your initial parameters, and if that still doesn't work, talk to your professor. While here it's very close to fitting the data, it doesn't quite fit perfectly. This program makes it easy to get a more exact fit. This number that says RMS residual is a measure of how well your curve fits your data point. The smaller the number, the better the fit. The number is in scientific notation, and that can be a little confusing if you're not familiar with it. So the program uses red and green to help you recognize when the number gets larger or smaller. If you have trouble distinguishing red from green, your instructor can help you understand the numbers better. We start with the course setting, and we click one of the arrows to the left or right of the top bar. If the RMS gets larger, the number turns red. If this happens, keep clicking in the other direction until then the number turns red. And then for the moment, that bar will be optimized. Click back till it turns green again, so the smallest number. You can make note that if you go to either side of this green number, it's going to be red. Then you continue to the next bar and repeat the process. And then you continue to the bottom bar and repeat the process. Then you go back up to the top bar and do it again, the middle bar and the bottom bar, and you keep doing this process until none of the bars are changing anymore. You can watch here as I go through the process. There, now I've done it. That's probably good enough for this lab, but we can do even better. Click to where it says fine, and we can do a fine adjustment, and repeat the process until again the bars aren't changing. Now it is truly the closest fit that you can get with this program. Now we want our best fit period, which is right here in the box that says period. Record this value in the first column of data table B at the end of your lab handout. Also record the amplitude, which goes into the third column of the data sheet. Be sure these are entered in the row for the moon Ganymede, because that's the one we're working on right now. You can pause now and finish getting your values for the moon Callisto, and then continue on when you're ready to go to the next moon. Okay, moving on to the next moon. This time, select Callisto. Notice that Callisto does not make a full orbit in the time that we were taking data. Depending on exactly what year and what time your data was taken, there are several different ways it might look. In this example, there's no point where it crosses the x-axis while going upward. Okay, I'm going to connect the points now. I'm going to, with my mind and with the arrow, kind of estimate where it would cross. Then I'm going to click that point. I need to open up the initial parameters box. And I will enter the x value for that point. If your data has the line already crossing on the way up, then you just take that actual point. You don't need to estimate where it would cross. Next, we need to find a half period. One way to do it is to find the time between two places where it crosses the x-axis. Another way to do it is to find the time between where one of the highest and lowest spots on the graph. I'm going to do it the first way, finding the time between where it crosses here on the way down and where it crosses on my imagined position on the way up. Then I will take the difference between those two values as I did before to get the time for the half period. Since this is a half period, I have to double it to get the whole period. Then I enter this value as the period. Oops, I entered the wrong number. I wrote 14.8 instead of 15.8. Let's see how that affects things in the end. I'll find the amplitude like I did before by finding the largest value of the highest and lowest points. And I'll enter that value in for the amplitude in the initial parameters. I click OK, but I see that my curve is a little off in period. The points fit on one side, but not on the other. So I can go to the bar that adjusts the period. And I can just click and drag it and adjust by eyeball. Any parameter can be adjusted this way. If I want to recenter the square, I can just click these little arrows to the side. Then proceed with the adjustments like the previous moon. Pause here until you're ready for the next moon. Next, let's do Europa. Oh my goodness, it looks complicated. It will look better when we just connect the dots. It's not as nice as before, but we can see that there's a little over 2 periods, and we can work with this. Find the first place where it crosses the x-axis on the way up, and click that point. This is our T0 point. We need to make note of that point and enter it as our initial value for T0. Now, you could just find the next time it crosses the x-axis on the way up and then get that as your estimate for the period. But to get more accuracy, you could actually try to take in more periods, like in this case, 2 periods. So I'm going to trace 1 period, 2 periods, then I'm going to click that point. And I'm going to find the difference in time between that point and the T0 point. But this is for 2 periods, and I want to find just 1 period. So I divide by 2, and I would enter that value for the period. The last moon, Io, is the hardest. I'll let you figure that one out on your own, but ask for help if you need it.